Shmooball for a reason? Man, that's really depressing. You're not getting them next year, okay? Only people that haven't been to Shmoocon before get Shmooballs. That doesn't count, man. That's more like automatic, you know. That's like a Make magazine kind of problem. Haha, check. All right. Anyway, these guys are going to talk about blowing up the internet, and all the series of tubes are all going to get plugged up and explode. Anyway, it's great to have these guys here and make the trek and have some really neat stuff to talk about. So I'm not going to take up any more of their time. Good luck, guys. I'm going to follow my wife that way. So.
Hopefully, yes, this works, so obviously. Hi. Once again, we're happy so many people are here. This is Daniel, I'm Enno. Probably some of you already know us from recent talks. That's why I won't introduce us in a very lengthy manner. We already had this today, so let's just skip over this. Our talk is going to cover, say, technologies that are not used in everybody's local area network, be it at home, be it in company, local area networks. So some protocols, some technologies which are mainly used in carrier space for various purposes. Still, everybody's life is kind of affected by these technologies. And we are going to, say, expose weaknesses in the trust models. We will demonstrate a number of attacks. All these attacks have in common that they are based on some assumption that somehow the trust model that exists is violated, and after this assumption the attacks are possible. You will later understand what I'm referring to here. And that's the connecting point between the three technologies we are going to cover. That's BGP, that's MPLS, and that's some new shiny service. It's not really a technology, it's more or less a service sold by carriers called Carrier Ethernet. Again, that's the common denominator is they're running the backbone and they have some so-called trust model. That's why I'd like to stress out there are several dimensions in our talk. I mean, obviously it's Shmoo, it's about attacking, it's about showing how to attack, it's about demos and stuff, but there is something else in it. We want you to reflect on some abstract entity that we call trust model. We want you to understand that maybe assumptions why you think your networks are secure, those assumptions may be justified or they may be unjustified, and think about this. That is one of the reasons for this talk. The other one is, entertaining you, Shmoo time. And some of you working in large organizations will be confronted maybe on a day-to-day basis with stuff like this. You might notice the security excuse bingo, like, oh, nobody has ever done this. Oh, that's completely theoretical. We won't be affected. Stuff like this that some of you might have to struggle with on a, say, maybe daily basis in your corporate life. And so this is a third dimension. At some points we will inject some of these bingo bullet points, like, okay, this is usually where you will hear in your company something like, oh, this is completely theoretical. And we are trying to put some practical pieces into that theoretical discussion. Okay, three technologies, three dimensions. I'll skip into the first one, that is BGP. BGP stands for Border Gateway Protocol, which is specified, the version that's before that can currently be found in the RFC 1771. It's kind of the glue that keeps the internet together. So all the major, say, carrier devices run BGP. They exchange their routing information via BGP. So without BGP, no internet routing at all. BGP has a kind of interesting trust model. I will stress this term a lot of times throughout my talk, so this is one of the first time. Interesting trust model that I'll cover in the next slide. And BGP was subject of a heavy debate last year. Some of you might have been attended DEF CON or PH Neutral in Germany, where two guys presented on how to abuse BGP to redirect traffic on a large scale. In fact, I think they redirected the DEF CON network. I did not attend, but I know what I did at PH Neutral. There they redirected the PH Neutral network. So BGP has been in a large public discussion last year, and maybe we will continue or ignite again this discussion. The way BGP works technically is there are so-called BGP peers. Those are usually the routers communicating to each other. BGP works over TCP and kind of relies on TCP. If the TCP session, the underlying TCP session breaks, the BGP session breaks and all the routes get lost. Walking over TCP is an interesting point, as this implicitly means it's not walking over multicast like many other routing protocols do, which in turn means for an attacker it's not that easy like with OSPF to join a given set of BGP speakers. And it's not easy to spoof. Once those, say, BGP peers have established their relationship, it's like they tell each other, oh, I know that some network can be reached via my device. So I have some traffic, I have some reachability information over some about some given network. And this is called the NLRI, the network layer reachability information. And once they have exchanged those NLRIs, they take the information and calculate the traffic paths. Like, okay, on an internet scale, if I want to reach that or this prefix, that or this network, I can do so by going through the network of KPN and then traversing the network of VZB. And after that, there is a network of some local US-American provider. And to get there, I have this given path. And once I want to reach somebody there, traffic should flow in this direction. This is, in a very short manner, a description of BGP. The trust model underlying BGP is, I mean, it's given it's TCP based, it's usually configured either manually or by some sort of script. There is no, like, say, auto joining or auto configuration, which might happen with other routing protocols. Like they are, once they are enabled, they multicast and they join each other and they exchange information. That's different here. This means that usually, as for BGP, there is something we call intra-operator trust. The model is that the operators trust, one operator trusts that the other operator does his work in a reasonable way. And there is no extra, say, checking or something. It's usually, there are slight differences, but usually it's like, okay, I'm an operator, you are an operator, I trust you. So let's establish, I let you establish a BGP session with me and tell me some routes and so on. Given this, say, human-based factor, from time to time it happens there are incidents like in the 90s there was the so-called AS7007 incident where some, I think it was Midwest or some American regional provider announced reachability of the whole internet through his network. So all the traffic from all over the world flew into that American provider and overflowed his network, and the internet kind of was unreachable. And some of you might know the YouTube Pakistan incident. Last year, Pakistan on the national level wanted to block YouTube. They did this by BGP, and that information leaked kind of into the global routing tables of the internet, so YouTube was unavailable for some time in some networks. So it's all about some club of carrier personnel working together. Once you join that club, you might perform all sorts of nasty stuff. That's what the guys, Alex Pilosov, is by any chance, Anton or Alexis, some of you here? Then I mean that was great stuff. Alex Pilosov, I think he runs a provider in New York, so he is part of the Old Boys Club, is accepted as a member, and can subsequently speak over BGP, which most of you or I won't be able to speak BGP with those routers, as we are not accepted as, say, trusted peers. But once, I'll get back to this. There is, within BGP, there is some additional security mechanism, which is an MD5 signature, that actually is not part of the BGP protocol, but is part of some specification putting it into TCP, and BGP uses this kind of enhanced TCP. It's MD5, but the recent problems described of MD5 do not apply too much to BGP. So this is not a problem that it's MD5. But the trust model might become a problem once you're part of the club. So enough of the theory. We coded some tools. We have prepared some demos. In my introduction, I said the common denominator of this talk is that we somehow work based on some assumption. And the assumption now is that we are part of the Old Boys Club. That must be clear. It's not like what we are going to show now can be performed by any of you from his or her home DSL account. You have to be an accepted member. Once you're an accepted member, you may do all kinds of nasty stuff, and we have prepared two new tools that can help researching stuff like this. The first tool is called BGP command line. It can be used to manually inject routes, and it can be used to manually brute force MD5 keys. To give you an idea of what we are talking about, I'll show you. I'll show you the routing table of the router I'm connected to now, which looks like this. There are some routes in there. I won't discuss them in lengthy detail here. You just have to know those routes are called C routes, connected routes, and an O route and OSPF route. So there is no BGP route currently. We will now use the tool that we wrote for proof of concept purposes. I think we switch over to you. Keep this in mind, so no route so far. You want to use this, or should I pick the other? I can do it like.
Okay, so next step is just I'm now directly connected to our router next to me, and I'm going to start up the BGP command line interface and just simply set up a session to that router. So I need to create a session. Both parameters are my autonomous system I'm going to pronounce, and the second one is just a hold timer. I use a very short hold timer just for demo purposes, that if we send some wrong package or lose the connection, that we don't have to wait that long for reconnect. Okay, so the next step is I need to connect my BGP session with the router next to me, and so this is what I did now. I just got connected. In the background there is keep alive thread started, so BGP keep alive packages are being sent out all the time. And okay, now I'm a valid BGP speaking neighbor of this router and can insert every BGP route I want. So this is called BGP command line. So I need to prepare my BGP update message like this. So you got a BGP update message with a few parameters. One is the next hop attribute that says, okay, the route I'm just pronouncing is delivered to you by this host, and all packages to the net following, please send to that host. So that's actually my IP address, and I'm going to pronounce this net the 10.0.0.0 square 8. Okay, so once I prepared this update message, I can send it out, and the update is sent. And if we switch over to Enno's PC again, you will see there is a new route spawned in the routing table.
The one of the B, this one.
Which says, okay, the network 10.0.0.0 square 8 is connected via the host 172.16.02, and I got this route via a BGP update.
So it's possible to manually inject BGP routes, which is not that spectacular so far, but still, to the best of our knowledge, there haven't been tools around for this in a say, command line fashion.
So, okay, this was really easy. What's next? Typically, BGP speaking hosts are secured by an MD5 password or authentication. So I just need to set myself another IP address. Now I'm a different host. I'm a different BGP neighbor. This BGP neighbor is configured with an MD5 secret. So if I just try the same over here, okay, I create a session, and I try to connect to the same host. Then these connect will, after a while, fail. Okay, we got a timeout. Let's have a look on Enno's PC.
Basically, I mean, the fact the connection did not come up was due to a failed MD5 authentication. So there is some added security control here. It's not like I accept once I accept a peer as it is pre-configured and get all routes. No, the peer that is pre-configured has to dispose of the right MD5 key.
Okay, so the next step is that we try to brute force this MD5 key, and we got a little nice command in the command line, which is the MD5 brute force command. And I'll supply a word list, and after I enter that command, the tool will just start to guess the MD5 password, and you see it's really slow. You have to wait for the timeout of your TCP Connect, which is at least 1 second. So this is not the way we want to go.
I mean, it could be done, but I mean, it's slow, and we will see it gets heavily noticed on the other device. But still, it might be a valid way of trying to get into a BGP network, again, based on the assumption that you are somehow already configured as a peer.
Okay, so we will do this MD5 crack in a more efficient way. And for that we need one correct signed packet from the other router. Okay, we get these packets all the time. So, because as you see, I got a Wireshark in the back. This router is trying to get a connection with my peer, so he sends me MD5 signed SYN packages. As you see in the TCP header is an option field called TCP MD5 signature.
So we don't even have to say stress this packet. The other one might send it out anyway, or we might be able to sniff it somewhere from the wire.
Okay. Once we got this packet, there is another cool tool I coded, which is called BGP MD5 crack, which just do a word list attack against a sniffed MD5 signed packet. This can be provided either via a PCAP file, or you can sniff live on an interface, and the tool will get the first signed packet and just brute force it. So when we start this tool, it will just take about 7 seconds to guess the whole 50 megabyte word file. And after that, you see we got lots of tries in these 7 seconds, and we found the right password for this connection.
Okay, so far for the BGP, which is the step here. I mean, all this is not, say, spectacularly new. The point is, there haven't, the bingo field applied to this would have been, oh, this is completely theoretical, nobody has ever done this. So now there is a tool available that can help to perform research on, security research on BGP. By the way, you might, within the session, you see all the failed MD5 packets. You go on with the other demo now? You prepared? Yeah. So the point here is we have, based on the assumption, we somehow got into the network. We won't discuss how we got into the network, but based on the assumption we got into the network, we now have, say, a tool set to either inject routes manually or to be able to brute force or crack MD5 keys used in the BGP communication. For completeness sake, this is from an audit we performed some time ago. So the MD5 keys used even in large corporations or large environments not always are the best. I will go on with the next technology, and that one is, I mean, honestly, this is the part of the talk that the both of us like most. This is another technology, some of you might know it, MPLS. MPLS stands for multi-protocol label switching. It's a technology used to forward packets based on labels. So it's essentially like take a packet, put a label on it, and then forward it within a given infrastructure. And in that infrastructure, all the subsequent forwarding is done based on that label. So no more costly routing lookup, no more say IP destination-based routing, but just look at the label and this or that direction. Almost every carrier backbone uses MPLS to some degree in the meantime. And within MPLS, MPLS is say a collection of technologies and protocols. There is one technology that's particularly interesting, that is the so-called MPLS layer 3 VPNs. Those can be found in most large enterprise networks. In the meantime, it's not like they run it themselves, but they buy, say, an MPLS VPN service from some carrier. Imagine some organization running a worldwide network. They connect all the worldwide sites by means of a carrier backbone where MPLS is used. These MPLS VPNs have a whole own terminology and own concepts and own associated protocols. Some people compare them to frame relay or the ATM in the sense that there is a shared carrier backbone, and over the shared carrier backbone you have separated routing of different customers. It's like Coca-Cola and Disney and McDonald's all run their global networks, maybe on the same physical infrastructure, but their traffic is separated by means of these labels. So it's like, okay, the blue label is for, say, IBM, the red label is for Coca-Cola, and the yellow one is for McDonald's. The terminology used usually is that of so-called PE routers that belong to the carrier and CE devices that belong to the customer. And this space here usually is under the control of the carrier, which is not, there might be exceptions like very large organizations running their own PEs. Even though most carriers neglect that this exists, but it's out there. But essentially, you can say, okay, we have a customer space and we have a carrier space, the P network. And on those routers of the carriers, they are called the PEs, provider edge devices. Usually, you have different routing tables for all the customers. Like there's a green routing table for, say, Chrysler, and a gray routing table for some other organization. Oh, by the way, we are going to use different customers in our demos. There's one, say, imagine network Shmoo and a network Ball. I'll introduce in a second. So the green one might be the Shmoo network, and the other one is another customer, the Ball network. So there is virtual routing tables for the customer. There's a global routing table for the backbone. And it can be seen like this. So we have a yellow organization and a green one, and they communicate over the same infrastructure. And this infrastructure is run by some provider, some carrier. I will skip this in detail. The main point here is that labels do the whole VPN thing here. The traffic segment separation, one customer, another customer, is solely based on the label. Which means that the trust model, the underlying trust model is, it is assumed the carrier network as a whole is secure. And this is the concept of a trusted core. Technology-wise, attacks from outside of the core are not possible. This is a given. On the other hand, within the core, usually there are absolutely no additional security controls. MPLS does not dispose of any, say, integrity checking or validity checking or whatever. It's assumed MPLS is run in a safe network, and customers connecting to don't have any access to this network. So the trust model is a very simple one, trusted core and the rest. This trust model is usually a source of grim debates in some organizations between the security people and network people, as one security people bring up like, oh, so there is no encryption, there is no integrity checking, there's essentially nothing in the core, which means we have to trust the carrier. As we can't enforce security on our own, it's usually like, oh, nobody will ever try to do MPLS-based attacks, or you're paranoid. This is what I'm working in such kinds of organizations, and I'm on the security side, and this is what we usually get to listen to. That's completely theoretical, and why shouldn't we trust our carrier anyway? Once you trust your carrier, we are okay with that. We just want to point out that maybe if you have a slight mistrust, you should think about the attacks, and you should know there are some new tools out there. We essentially, Daniel wrote a tool that's called MPLS Redirect, and this one assumes the attacker has somehow access to a traffic path in the core. Again, this may be a valid assumption, or it may be invalid. I can tell you, I've been working in carrier space for a long time. I have performed pen tests and audits, and the security of carrier space is not better than the security of, say, a large enterprise space, whatever this means. So you can imagine what this means. It's a command line tool, and this one modifies VPN labels of packets while traversing the backbone. Maybe we should give you a demo. In this demo that we are going to show, it's assumed there are two networks. There's a yellow one, customer Shmoo, and a green customer called Ball. And they are running their worldwide enterprise networks by means of MPLS over some shared carrier infrastructure. We have prepared. Okay. We had to reload the system. The point is we need a certain set of labels that in our very small test environment might not appear as such, but which can be found in every, say, real life MPLS okay, so far we have, yeah. We have to wait till one information exchange of the involved devices has finished. No labels so far. Again, it works a bit like this. I'll use the time to explain what's going on here. Those devices, the PEs, once the customers get connected, tell each other something like, imagine this one. This PE tells the other one, if you want to send me packets that are destined for the green customer, as opposed to the yellow customer, and these packets are destined to a given prefix, like 172.31.2.0, you should label them with, say, label 20. If I get packets from you that are labeled 21, they belong to the yellow customer. So that's why we say the whole VPN stuff is based on the. Okay, again we have the unfortunate position that there are two labels that are the same, and this is the only case where our demo does not work easily. Okay, I will try. Okay, we will see what happens after the. I reset the BGP session now. Again, you see BGP is involved. So the technologies we cover in our talk are somehow they are built upon each other. They need each other for different purposes. By the way, this is a command clear IP BGP star that may lead once you perform it on the live router and the internet. May lead to being fired from your job. As this essentially clears a BGP session, which means all the routes get lost, and the carrier devices, usually they carry 200,000 and more BGP routes, so it takes some time to get up again the session, and during all this time the traffic is not able to flow. So no labels yet. What do we have here? Okay, session has to rebuild. Obviously, the demo we would really like to show is built upon modifying these labels, which essentially means now, okay. This is, I mean, when I was younger, I had a mentor who told me, whenever something goes wrong in a presentation, demo doesn't work, the main point is to keep cool and to go on. And but we are lucky. Now we have a state this demo might work. Oh, it will work. It will work. Okay, the scenario is, again, look at this. We have two customers connected to the same MPLS backbone, which is the usual case it is done. Currently, my laptop is placed within one of the customer networks. I'm in the network Shmoo, which means I can ping myself from this device by my IP address. Here we go, just to give you an idea. That was really me. I will fire up Wireshark to prove that I essentially received the packets. Okay, that's the correct adapter. Once again, we'll have a ping. So here we go. This is the ping has arrived. Again, I'm setting network Shmoo now. Once I switch over to network ball, I'm in another customer network now. I shouldn't be reachable anymore. You see, it doesn't work. I'm no more pingable. But I might be pingable in the network ball. Here we go. Which means now I'm in the, say, from here. I'm reachable in the green network. I'm sitting here now. Whereas before I was sitting here. So guess what is going to happen? We will show you that the traffic can be redirected, that traffic that is destined for the yellow network effectively ends up in the green network, just by modifying labels on the fly. Okay, Daniel, then it's your part again. Just to make sure. I'm in ball now. I'm not in Shmoo. I will be kind of in both networks afterwards. I will traffic destined for both. Yeah, take over.
So, next, I use a tool which is called MPLS Redirect. It's a small C program I wrote. So what it does is it just listens on an incoming interface, which in this case is interface bridge 0 and bridge 0, and sends package to an outgoing interface, which is bridge 0 again. Okay, with this instance of the tool, I relabel packages with an incoming label 17 to an outgoing label of 18. So this is one instance. This is one direction of traffic flow. I need to spawn another instance which relabel incoming labels 20 to outgoing label 90. Okay, so once I launch these two instances,
the following is going to happen. So again, remember, I'm in ball now. I'm physically in ball. And I'm still reachable in ball. But what happens if traffic is flowing through network Shmoo? I get it. So thanks for that. I get all the pings and I reply to all the pings. So we have a bidirectional traffic redirection. All the traffic going to one customer is actually branched. I was told that I have a strong German accent and I shouldn't use the word forked. So the traffic is branched. All the traffic flowing into one direction goes to another customer network as well. And the nice thing about this, I mean, it's nice in itself, but nobody will ever notice. You won't be able to detect this attack as, I mean, there is no integrity checks, there is no checksums, there is nothing in MPLS itself. So, yeah, traffic redirection on a large scale, based on the assumption we somehow got into the core or hacked the router there or whatever, but this is the thing. I talked about this attack in theory, and I showed it with manually modified packets at Black Hat 06 in Amsterdam. And ever since then, I was confronted with like, oh, that's theoretical, nobody will ever do this, all the stuff like this. And now, I mean, we have a tool that does this, and it's no more theoretical.
Question?
Yes?
Do the labels show up at the CE, or is it stripped off at the
It's stripped off. At the CE, you won't ever see any labels. By the way, I mean, the labels that Daniel used can be shown like what we did. I mean, those are, he replaced an 18 with a, oops, that was the wrong command. Where's the one? Yeah, that was the same one, I know. I should be able to, yes. What we did was we modified those labels belonging to two different customers. So what does this effectively mean as for attacks? Once an attacker gets somehow into the traffic path of MPLS, I mean, it's not only about redirection, it's about injection too. Obviously, we could create packets and label them. We do not have to rely on existing traffic, but we could join any given VPN. Once we are there, we could jump into the Coca-Cola network or the McDonald's network or the Chrysler network, everyone. Any of those networks we could send traffic to and ideally get the traffic back. So we can say do whatever this provides, like say put up a fake central authorization portal of company A and redirect it to the same looking piece in a completely different network. People enter all their authorization or authentication tokens, whatever. Same for DNS, same for directory services, whatever. DNS will be particularly interesting. Imagine the case all your company internal DNS lookups got redirected to another DNS server, which then serves back all the answers. I mean, there is no, say, limits for imagination what can be done with this. Yeah, that was, I mean, talking about mitigating controls. It's, I mean, trust your carrier. Once you do this, you're fine with that. If there is the bingo bullet point, we think it is secure enough, that's okay. We just want to raise your awareness. The whole security model is based upon labels, which are transported in some to-be-trusted space. Once the space is no more to be trusted, it's easy, very easy, with some tool to do harm on a large scale. Another approach could be to authenticate everything, but then it's like in large organizations, you usually have that approach of trusted networks and lesser trusted networks and untrusted networks labeled with different colors, and all this concept would be gone and once you have to authenticate every traffic flow. Usually you expect some traffic to come from trusted networks. Another approach could be implement borders of trust, say every traffic entering one site should be encrypted and authenticated, but then I mean, you lose all the, say, cost advantages of MPLS over IPsec, which might have been there before. So I'll get on to the third technology we are going to cover, that is Carrier Ethernet. Carrier Ethernet, just to make sure we are on the same page, basically means that Ethernet frames are transported across some carrier backbone. It's not about connecting by Ethernet. I mean, most of you will have their, say, WAN connections built with Ethernet, like there's a plug and you plug your router in, and I mean, that's Ethernet on a physical level. But carrier Ethernet means Ethernet, the frame, put on one side, travels across carrier backbone and gets out on the other side as an Ethernet frame with all the Ethernet attributes it might have had when it entered, like VLANs and like Ethernet addresses and stuff. This is a bit the product name, Carrier Ethernet, and usually the underlying technologies might be something called EO-MPLS, Ethernet over MPLS. So then MPLS provides the backbone for this. Like, again, it's labeling. Take Ethernet from customer McDonald's, label it, put Ethernet out on the other side, and encapsulate it. Take Ethernet from Coca-Cola, label it, encapsulate it, so Ethernet is not, it's preserved like an Ethernet frame, and put it out on the other side. There are other technologies, namely so-called Metro Ethernet, which can be used. The structure is always the same. It's like Ethernet frame in on one side, Ethernet frame out on the other side, and those two networks have the idea they are connected directly. You won't be able to see that there is a carrier backbone in between. It's like, okay, it's a shared LAN then, except for the fact that the LAN might be separated, the parts of the LAN on a worldwide scale. Interestingly, again, there is a term we regard as important when discussing these technologies. It's about trust models. And the trust model of Ethernet usually is like based on a site level. The mindset of people talking about Ethernet security is, okay, we have Ethernet security in the headquarters, say in Washington, D.C., and we have Ethernet security in some branch site in Seattle, or we have Ethernet security over there in Costa Rica, and Ethernet security over there in Germany. So Ethernet is something that happens on a site level. With carrier Ethernet, this model changes completely. It's like we have one large Ethernet that spans the globe, and within that Ethernet, there might be a zone of different trust, a carrier network. This brings up all sorts of implications. One term that might be interesting for a security discussion is the one of what I call full versus partial transparency, which essentially means full transparency means everything that gets in on one side gets out on the other side, which means a spanning tree, which might mean VTP, which might mean ether channel negotiation. All the stuff going in on one side gets out on the other side. That means carrier behaves completely transparently. This is not always the case. Depending on the carrier, on the devices used, on the technology that is underlying, and on the configuration, so a lot of parameters, it might happen that you find partial transparency, that some layer 2 packets get dropped, like spanning tree. Not everybody wants a spanning tree to happen over the cloud. But let's assume full transparency. There are all sorts of security implications. I'll name some here. The existing threats from the Ethernet world might have a completely new scope now. It might be like, okay, you can upspoof traffic that is located on the other side of the world. Because, I mean, it's global unified Ethernet. Misconfigurations will have much larger impact. Somebody does to perform some misconfiguration on some switch in Costa Rica might mean your switches in New York and the headquarters go down. And there might be new threats that show up. The current space of Ethernet protocols, they were never designed to work on a global level. They were designed to work on a local level. And that's what their trust model is built around. And again, all the stuff is running across some carrier backbone. And this carrier, again, has to separate traffic from one customer from traffic from the other customer. And the technologies used for this might not be the right set of technologies. So we will give some examples. This is what we once did in a test bed. In effect, I took this slide from my Black Hat Amsterdam talk. Who of you knows the tool Yersinia? Layer 2 attack tool. Oh, I had hoped it were more people, but I mean, I am a network security guy, so my perception of how important these tools are might be wrong. Yersinia is, say, the Swiss Army knife for performing all sorts of Ethernet attacks. And we used Yersinia over simulated the carrier cloud and could upspoof traffic between servers on one side. In this example, we call it Amsterdam. We could upspoof from another side, that's Brussels. So even though you might have, like, okay, in our headquarters, we have 802.1x, and we have good security controls on the Ethernet level. Now it might mean, oh, do they have in Costa Rica in that plant the same security level as for Ethernet? Once you use those technologies. And I can tell you they are rising. Market shares of this technology is going up. There are more and more organizations using this for, say, SAN replication across between data centers. And all the virtualized mobility stuff, like moving servers around, is heavily, can use those technologies. But this is, say, a customer problem. One could say, yeah, I mean, they do not their homework in the correct manner, so their problem. Another piece would be we could, say, perform all sorts of Yersinia attacks over the cloud. Do we have a Yersinia? Do you get a VTP? Like, we have connected to systems, to different sites. I have some special devices here called Metro devices. Those are not common Cisco's, but they have a ME in the name. And we effectively build a network that is one device, this small Cisco 2940 on one side, and the attacker sitting on the other side. And hopefully, we will see that the switch on one side spits out VTP packets, which is a Cisco proprietary protocol used for administering VLANs. Once it does so, hopefully, I mean, VTP packets are sent usually every 5 minutes, so I have to, yeah, that is a good point. Again, what we see here is the attacker's console on one side of the global cloud, whereas the device that is going to be attacked is on the other side of the global cloud. Now, just test. Okay, so we should at some point see the VTP packet Shmoo crossing the cloud. I mean, if that one doesn't work, that would be not that disastrous as we hope. It's pretty much okay. Yeah, Yersinia is a bit unreliable sometimes. I mean, it's always unreliable, but it's a pretty neat tool still. Okay, yeah, I mean, let's skip this one. We have another nice piece in our demo set for the sake of staying in time. We will skip this one. The idea, again, is perform attacks over the backbone. That is one thing that should be considered when using such technologies. Another one is there might be misconfigurations in the carrier backbone that lead to the fact that traffic from one customer comes out at another customer. Same stuff like what we showed with MPLS, but now it's not based on an attack, but it's based on some misconfiguration. For those of you who have been following the network Ethernet security space for some time, this might remind you like, oh, this is like the native VLAN stuff which could be found in, say, 2003 or 4. which was discussed at that time. Yes, this is exactly the same stuff, but now we have a double VLAN. There's a technology called Q and Q, where VLAN tags get, customer has VLANs and carriers have VLANs, and so packets carry two VLAN tags. No demo for this one, as it would have meant we had to reconfigure the devices. But this is a problem which is existent. A short wrap-up on carrier Ethernet. This is an interesting technology. As networkers, and I'm an old school networker, I mean, I like this stuff. But it changes the whole trust model of Ethernet, which might have large security implications, and it might even open the road for new attacks, like you might remember from the MPLS piece that we are able to inject traffic into sites. So what about injecting ARP responses into a site, which effectively means traffic that was supposed to stay within one site would leave the site? Like, again, bingo, Mr. Networker, global head of networks, oh, we encrypt, we have application layer endpoint encryption for all the traffic going over the cloud. So everything that leaves our site is encrypted anyway. Yeah, mister. Nice. But we can force traffic that was supposed to stay within one site out of it by injecting ARP packets. This will be, we hope to implement this for Shmoo next year. So nice security implications. Before we finish our talk, we have some demo left. Those who are still to some degree able to follow us. Remember the MPLS piece. What we did in the MPLS network was like modifying labels of packets traversing, say, the network, which means we have to touch every packet. But remember, there was some, what we called multi-protocol BGP, which is responsible for signaling this information about the meaning of the labels across the cloud, like one PE tells the other, listen, dear peer, if you send me packets with a label 20, this means I will forward them to customer Shmoo, whereas if you send traffic with label 21, I will forward them to customer ball. Now imagine what would happen once we modify this signaling information. It would mean we can modify, say, the global intra MPLS routing table, and we would have to do this only once, not for every packet. We might be able to, say, put up bogus sites, like showing up within a given network, like, oh, were we supposed to have a site in Costa Rica? We never knew that. Why is that site in Costa Rica announcing our DNS server is sitting over there? Stuff like this, which means traffic redirection and stuff on a site level without much effort, just by injecting bogus multi-protocol BGP. Again, we have prepared a demo for this. I'll show you the routing table for customer Shmoo. Remember, this was this one. Customer Shmoo has in the routing table used within MPLS. There is essentially just two networks: 172.31.2.0 and 172.31.1.0. Now Daniel again uses the BGP command line, which we enhanced by this special so-called multi-protocol BGP capabilities. This will be a bit not too readable command we use now, but okay, I got something.
This is the update package.
Yeah, we won't annoy you with the exact meaning. We will just show what this means in the routing table. Now we have a new entry in the customer Shmoocon routing table, which essentially says, oh, there's a new route for the system 172.31.2.100 going to some way. So this might be corporate DNS server. And now all the traffic destined to corporate DNS server goes to some phantom site in Costa Rica. And once this is, I mean, we don't have to interfere with the traffic flowing on from now on. We just have redirected it by modifying the routing table. Yeah, nobody will ever try to do this. So. Some fun with multi-protocol BGP. Okay, summary and outlook. What we wanted to make you aware of is that those technologies used in in carrier backbones and used by large customers rely on some trust models. We want you to think about those trust models. And that's essentially all we wanted to achieve. Thank you. I know we are over time. I'm willing to accept. Get back to me if you have any questions on this. But we hope you forgive us going over time with this stuff. Thanks again.
Sorry for that. I know that the advantage you have open.
What's that?
You have open end.
Oh, yeah.